Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 46, and this problem asks us, in these two pairs, which molecule in each pair is a stronger acid? So what do we know about acids? Well, acids give up protons, so they're proton donors. So they will give away their proton to a molecule. And what we know about something that's a stronger acid, well, we know that a stronger acid will have a more stable conjugate base. So let's draw what happens if we lose protons out of these two molecules. So now we lose a proton here, so we get a carbanion. And then in this structure here, we lose a proton, so we also get a carbanion. So now let's look. Well, we have resonance stabilization with this molecule because we can move around this carbanion to this position here and this position here. So this molecule is resonance stabilized, but it is not aromatic in nature because it's not cyclical. It's not a cyclic structure, therefore it cannot be aromatic. Well, what about this one? Well, this one's cyclical. Every single bond is sp2 hybridized. It is planar. So far, it could be a candidate to being aromatic, but we need to see if it follows the 4n plus 2 rule. And here we have 2, 4, 6 protons. So if n equals 1, then we have 6 pi bonds, or pi electrons, sorry. So this conjugate base is actually an aromatic conjugate base. Therefore, the stability of this is going to be greatly enhanced more so than something that is just resonance stabilized. An aromatic ring will be more stable than a resonance stabilized ring. Therefore, the conjugate base of this is more stable than this linear moiety here. Therefore, this is going to be more acidic because the conjugate base is more stabilized. Now, using that same logic, let's do the second problem. So the second problem, we have that same molecule. So we already know this is going to be aromatic. And then we have now a cyclopropene. So now let's see, we already know this is aromatic with 6 pi electrons. So now let's check out this molecule here. Well, this molecule has 4 pi electrons. We have 2 from that pi bond, or from the double bond, and 2 from the lone pair electrons here, because they exist in the p orbital. So now let's see if it follows the 4n plus 2 rule for aromaticity or the 4n rule for anti-aromaticity. Well, clearly we see that it follows the 4n rule for anti-aromaticity. So this molecule is actually anti-aromatic. And what we know about something that's anti-aromatic is that it is highly more unstable than a resonance stable molecule or even than an aromatic structure. So we know that anti-aromatic structures are unusually not stable. Therefore, because a conjugate base is unusually not stable, this cannot be more acidic than something that is aromatic. Something that's aromatic is significantly more stabilized. Therefore, once again, this is the better acid.